Okay, thank you so much to the organisers for having me at this really interesting and broad meeting. I'm going to talk about some work I've been doing with my team at UCL. I'm about to move to Durham University just next week, actually, but most of this work has been done at UCL, and it's all about the way that galaxies are really an interplay between the particular history of the way that that galaxy built up over time and the internal processes of feedback that regulate the way that that galaxy forms stars and changes over time. And we have a cool name for this. We call it genetically modified galaxies because everybody needs a cool name. I'm going to explain what that's all about, first of all. And then rather than try and show you everything we've done, I'm going to particularly dive into some stuff about dwarf galaxies for the time that I have available. So just to take a step back about what we're doing, I think it ties into a lot of the themes that have come out this morning already. The fact is that, structure is supposedly formed by cold dark matter, and that's proved an excellent paradigm for understanding the overall formation of structure in our universe. But one of the predictions of cold dark matter, the cold dark matter paradigm, is that the collapsed object should be roughly scale-free. That is, it doesn't really matter what mass of object you're looking at. It looks essentially the same. Now, if I put side by side cold dark matter simulations of objects at different masses, you can see by eye that there is some trend there, but it's a relatively modest trend, and moreover, a lot of that trend is just being driven by how dynamically old these objects are. So the smaller things, on average, collapse earlier in the history of the universe, so they have longer to dynamically relax compared to the big things that you would expect to host galaxy clusters. And so actually, there's really very little scale information in the cold dark matter universe. But by contrast, of course, galaxies are almost the opposite of that. First of all, they are incredibly scale dependent. So if you look at an ultra-faint dwarf galaxy, there's Leo 4 for you, you can't even see it, right? I mean, it's just, it barely qualifies as an object at all when you look at it like that. And yet we know that it is a bound object. But then you go through, beautiful spiral galaxies and up to ellipticals and then onwards to clusters and so on. Clearly, there's a huge mass dependence in the way that galaxy formation plays out. And we understand why that is, because baryons are not scale-free. And so you need to understand the interaction between the invisible cold dark matter world and the visible baryonic world. And even if you don't care about galaxy formation in its own right, you might want to care about this because if you want to interpret the observed universe with an eye to what is dark matter, then astrophysics is going to play a kind of systematic role in that. Also, as we were seeing yesterday from Alex's talk, it also plays a role even in large-scale surveys these days, with the way that material can be moved around by feedback on really very large scales. Another reason you might want to care about it is because you might be slightly concerned that actually a lot of what we see today is relatively high surface brightness galaxies. And there's a lot we don't know about what goes on down at low surface brightnesses. We currently have really quite a biased view in some senses of what is going on in galaxy formation. And the Vera Rubin Observatory and other facilities are going to change that. And finally, if you look further ahead in time, if we come back in 20 years, I think the entire field will presumably be turned on its head by then, because you're going to have facilities like LISA, like Cosmic Explorer or Einstein Telescope that are going to give you viewpoints on how supermassive black holes and also stellar populations build up in the very, very early universe to go alongside JWST. So you need to be ready for that kind of complementary view of the way that structure has formed. You're going to be able to see essentially all the way back to the beginning of structure formation in the gravitational wave domain. So there's a lot of reasons to care about how all of this fits together. Just to inject an exciting point of disagreement, I actually think this field is older than the Institute of Astronomy. So I recently had a lot of fun writing a popular book about this and tried to trace back some of the origins of the ideas that we talk about today. And in fact, in terms of galaxy formation simulations, the work of Beatrice Tinsley, so in her PhD thesis in the late 1960s, it's actually astonishingly prescient, thank you. It's astonishingly prescient, some of the stuff that comes up in the late 1960s, using computers for the first time to try and understand how galaxies form. And in fact, you know, if I want to be even bolder, I would say that this field is twice as old as the Institute of Astronomy, because if you care about numerical simulations, first person to do that was Lewis Fry Richardson. He was trying to do weather forecasts numerically, starting from the Navier-Stokes equations, using pencil and paper. Right, so he actually discretized things onto a grid, used pencil and paper to try and figure out weather forecasts, and came across all the problems that we talk about today, the problems of resolution, the need for a subgrid. All of these things are in Lewis Fry Richardson's book in 1919. And you know, he came up with this big problem. If we want to do weather forecasting, or in our case, galaxy formation simulations, how on earth do you get enough power, calculational power, to be able to do this? And actually, he had a really good solution. Hire loads and loads and loads of PhD students and put them in a giant purpose-built amphitheater. Then the professor stands in the middle and tells them exactly what to do. So if you zoom into this, in each of these little grid squares, you have some PhD students doing the calculations, and then they pass the results of the calculations on to their neighbors and so on. Gosh, history could have been so different, couldn't it? We could have employed a lot more people in our fields if only no one had invented the computer. Anyway, so we do have these problems of just always, you know, we don't really have enough computer power to do what we would like. And Julien has introduced this dichotomy between, do you zoom? Do you look at, you know, one or a handful of objects and put all of your computer power on those? Or do you try to run a large volume? And the fact is we sort of need to do both, because you need the sampling over different histories to understand the diversity of the objects you're getting. But you also need as much numerical resolution as you can possibly get in order that you begin to trust the results a little bit more. So the idea of this genetically modified galaxies program is to try in some sense to combine the best of both worlds by performing simulations that have controlled changes in their initial conditions and therefore in the particular history that unfolds for a galaxy. So if you look from left to right, this is from work from Nina Roth back in about 2016 or so. From left to right, we're going to have slightly different formation histories for the formation of a central galaxy. Here it is at redshift 17. As you go forward in time, you can see that essentially, you know, they're forming out of a cosmic web that looks very similar, but over time, small differences begin to emerge between the three histories. I don't have time today to go into exactly how we construct these. Of course, we can talk about that over coffee. And then the interesting thing to do is then see what actually plays out when you put this into a live numerical simulation and with all the feedback processes and so on that we've been talking about. And can you understand what kind of trends and differences emerge from this process? So just to flash up very quickly, you know, we've been applying this on a variety of mass scales, so the kind of Milky Way mass scale, looking at how the effect of different strengths of mergers at different times plays out. So here looking at redshift 0, a Milky Way mass galaxy, but it had a different merger up at redshift 2. And we look at this across different codes to get some idea of, you know, what can we believe, or what is more of just a property of the particular feedback recipes that have been introduced. And we also look at the effect of angular momentum. So if you have different amounts of angular momentum flowing into a galaxy, how does that affect its emergent properties? And then at slightly higher mass scales, you know, this connection between the black holes, the central supermassive black holes, and the history of a galaxy is also very interesting. And we've looked a lot about what determines, the central supermassive black hole mass, and by extension, the amount of energy that it's injected into the galaxy over cosmic history. But I didn't want to focus too much on that today. I wanted to focus right down on the dwarf galaxy scale, where some of the most interesting effects take place. Here we have some very high resolution simulations. They're about 3 parsec resolution, so that you can actually resolve the interstellar medium. You can resolve the individual shock waves from individual supernovae going through the interstellar medium. They also run with radiative transfer, so that you can see the effects of the ionizing radiation coming from the individual stars and from the extragalactic background as well. And you've just seen one of our simulations evolve to just pre-reionization. These things are so small that if you then go forwards in time, as reionization from all the sources in the wider universe begin to hit, the gas just evaporates away in the smallest of these objects. So these form some stars pre-reionization, but then they can't survive the UV field from reionization as a whole. Believe it or not, this video is still running. It's just that there is no gas left to do anything interesting at late times. Now, when you combine that with the genetically modified idea, you can take the same cosmic web, the same basic initial conditions, but modify them so that the structure collapses at a different rate, so that it's built up a different fraction of its final mass by the time of reionization. That's what's going on here. You're comparing 2 different rates of formation in otherwise the same galaxy. Now, I've paused it just prior to reionization. You see on the left, this built up a lot of its mass before reionization hits, and so it's actually been able to form a bunch of stars, whereas the thing on the right is still to build up a large fraction of its mass. So it hasn't been able to form those stars. And then when I restart the animation, of course, the gas all evaporates due to reionization coming in. And what you're left with on the left is a relatively bright dwarf galaxy, and on the right, a dim dwarf galaxy. In fact, these things differ a huge amount in their stellar mass, as I'm about to show you, but just to say that their final dynamical mass is exactly the same. So that's the sense in which this is a controlled test. It's collapsed from the same area of the cosmic web. As much as possible is being held fixed, and it reaches exactly the same final dynamical mass. But when you look at the stellar masses, they actually differ by an order of magnitude, just because of the timing of when this thing collapsed relative to reionization. So if you form your mass earlier, you end up with a higher stellar mass, and that's at a fixed dynamical mass today. So the idea that a given dynamical mass tells you what stellar mass you're going to end up with is certainly not correct at the low mass end. There is going to be a huge amount of scatter. And this is particularly interesting when you realize that actually even the redshift 0 mass of that lowest mass object is built up in a rather different way. It's built up through merging teeny tiny dwarf galaxies into the slightly bigger dwarf galaxy that you're forming. That happens post-reionization. So you merge a bunch of things that all have kind of small amounts of stars in them. And that leaves you with a dwarf galaxy that formed mainly from accreted stars. And those accreted stars are on wide orbits. So you end up with a very big, fluffy, no longer star-forming dwarf galaxy. In other words, a sort of ultra-faint dwarf galaxy, or in fact, that's like an ultra-faint dwarf galaxy. If you put this on a plot of the total V-band magnitude on the y-axis there versus the half-light radius, so something with a fixed surface brightness is on one of these diagonal lines here, then just by varying where this collapse happened, you end up kind of cutting across this in a diagonal line. And so, when you look ahead to things like LSST, there is a lot of interest in what are you actually going to find. And have very little time, so I can't really explain, but we have a program where we're trying to make statistical predictions based on a relatively small number of these simulations. So in my last 1 minute, I just want to mention that we're also interested in the implications for dark matter. So if you look at the inferred central densities of dark matter in dwarf galaxies. As Julien already mentioned, they are not always as high as the pure CDM prediction would lead you to expect. So this is something known as the cusp core problem. And you can interpret this as evidence for self-interacting or ultralight dark matter, some kind of exotic extension of the CDM paradigm. But it's been known for a long time that baryonic effects can actually make the dark matter migrate outwards. And so the question is, what does this kind of formation history affect? What kind of effect does having different formation histories have on the way that this process plays out? And the answer is that it has quite a profound one. I mean, partly you can look at this as just how many stars does a galaxy form, which is essentially what's being plotted here. So how many stars does a galaxy form relative to its overall mass on the x-axis, and what's happened to its dark matter mass on the y-axis. But actually, this work is on the archive today, by the way, from my PhD student Claudia Mooney. Much better way to look at this is not so much the total amount of stars that you formed as a fraction of the dynamical mass, but more about what does the star formation history look like overall. If you have a sustained star formation history that actually makes it past reionization, then you find that that's very effective at getting rid of the central dark matter cusps. Whereas something that forms actually quite a lot of stars, if it did it all around about the time of reionization, is not very effective at doing this. And I'd encourage you, if you're interested in this kind of thing, to take a look at her work on the archive today. So I'm out of time, so I will not explain in any further detail, but I'll just put up some conclusions and end. Thank you.